Sound. This is just the background information for things having to deal with sound. Here are some of the facts about sound. It is a form of energy that is transmitted by vibrating matter, so things that are going back and forth. It travels in waves, and it travels more quickly through solids than liquids or gases. For our purposes, the ear is what interprets sound, and sound is carried to our ears through vibrating air molecules. When I'm talking right now, I'm vibrating the air, which is then going to the microphone. Our ears are going to take in sound waves, and they're going to turn them into signals that go to our brains. There are three very important parts to figure out how we hear. The first is the outer ear, and the outer ear is going to collect the sound. Then it goes to the middle ear, and the middle ear is going to amplify it. And then the inner ear, which is the third part, is going to convert it into a message into our brain. If you've already had anatomy, or if you're in anatomy now, you'll be much more familiar with these concepts. Here's just a diagram of what each part of the ear does. So we have our outer ear, which is going to gather sound waves. That's its role. And that's why we've got this funky looking thing here. It's trying to gather in those waves. Okay, the middle ear, which is going to be the amplification of the waves, has a bunch of different parts. The wave comes in and it travels through the ear canal, and then it hits these little parts here in the middle ear. And last is the inner ear, and the inner ear is going to convert the waves to nerve impulses, which then go to our brain. Sound travels as a longitudinal wave, which means that it has compressions. Compressions are when molecules are being pressed together as the sound waves move through matter. If you look at the diagram at the bottom and we think of the slinky, a wave's going to travel through the springs just like sound waves. So we've got this area here which is compressed, and then the rest is split apart. As the sound moves through the wave, you can see that the compression, the compression is going to move along, and now the slings or the coils are going to end up spreading apart. And as we keep moving, it keeps moving farther and farther down, and that's how the wave is traveling through the air. When those compressions are traveling, what's happening is we're getting alternating areas of high and low pressure in the air, and sound is carried through matter, solid, liquid, gas, whatever, as a sound wave. So as that compressional longitudinal wave. Sound waves move in all directions. If you ever see a sound wave drawn, you might see it kind of drawn out like this, because it gets very, very big, because it's not just from in a certain plane. It can go in many directions. Sonar is something that uses sound waves in order to find objects. Typically what we know about sonar is that we use it in things like submarines. But sonar actually stands for sound navigation and ranging. What it does is it sends out a sound wave, and then it uses the echo. It's called echolocation. You may have heard of that. Bats do this. Some other animals do this in order to figure out how far objects are from them. So humans, we use it, especially in submarines, to map or locate objects, especially when a submarine is underwater. It can't always see what's in front of it. So it sends out and uses echolocation to make sure that there are no obstacles in its way. Pitch is a measure of how high or low a sound is. You've probably heard if somebody has perfect pitch. Excellent movie. And pitch depends on the frequency of a sound wave. So if it has, an object has low pitch, that means it's going to have low frequency. They are directly related. If it has a high pitch, that means it has a high frequency. So if something has a high frequency, it's going to have a higher pitch sound. If something has a lower frequency, it's going to have a lower pitch sound. in terms of humans, when we talk about frequency and pitch, higher frequency means that there are more vibrations hitting the air. We, as healthy humans, can only hear from about 20 hertz to about 20,000 hertz. It sounds like a lot, but other animals can do much more. We're very sensitive from the area of about 440 hertz to about 7,000 hertz. And there's a sound test you can do, which you can see, which hertz you can hear and which ones you can't hear and things like that. It's kind of cool. Some other properties of sound you've probably heard of: intensity and loudness. If something is very intense, it's going to actually talk about the energy in the sound wave. If it's got a lot of energy, it's very intense. If it doesn't have as much energy, it's less intense. Loudness is something that we perceive. It's not an actual measurable type of thing, because some people might find something loud and others might not. So it's actually a perception depending on the person. Loudness, though, can be measured, and intensity can be measured, and we measure these in decibels. So deci is, if you remember from your prefixes, and the bells is the standard there, but we call it decibels all the time, and you may have heard of it before. Here are just some common loudness in decibels that you guys are noises that you're probably familiar with. A whisper is around 15 decibels as we keep going. Average home is about 50, vacuum cleaners about 75, noisy restaurants 80. Our threshold of hearing is going to be 0 decibels, so that's the lowest that we can hear. The threshold of pain is about 120 decibels. Anything beyond that can actually cause us pain in our ears. So a plane taking off and a lawnmower is starting to get really close to our pain threshold. But that's why you guys should not wear your headphones and play them too loud, because you can be damaging your ears very much. So I said that humans can hear up to 20,000 hertz, and we call that the sonic range because that's our sound. If we go up into the ultrasonic range, though, ultra is going to be greater than. There are other things that you can use ultrasonic sound for. For example, we know that dogs can hear more than we can. They can hear up to 35,000 hertz. Bats can hear even more, which kind of makes sense because they're blind and they use echolocation for life. That's how they get around, because they can't see anything. You've probably heard of ultrasounds for a medical diagnosis. I had one last week on my leg, so that helps, and it kind of figures out where things are located, if there's something in the way when there shouldn't be. The opposite of ultrasonic is going to be infrasonic. Infrasonic sound is going to be something that's below 20 hertz. It's very, very low frequency. And typically infrasonic sounds are going to be felt rather than heard. So if you've ever walked by heavy machinery, you can probably feel it kind of pounding within your head. Earthquakes are an example of this as well. Okay, the last part I'm going to talk about today is just the speed of sound. And the speed of sound is always going to be 332 meters per second in air at 0 degrees. So that's pretty cold if you think about it. And it changes by 0.6 meters per second for every Celsius degree up from 0. So if we take this and we actually write this as the velocity of sound, we can take 332 meters per second, and then you add to it 0.6 times whatever the degrees Celsius is. And that will give you the speed of sound in whatever air the object is traveling through, or the sound wave is traveling through. That's about it for today, just the background on sound, and we will continue tomorrow. Have a great night.